All right, good morning, everyone. Today's lecture topic is going to be on virtual trees, also sometimes referred to as auxiliary trees. As the name suggests, it's going to be a technique that we can use on trees, specifically rooted trees, but anytime we have an unrooted tree, we usually just arbitrarily root it anyway. And what virtual trees are is they're basically just a fancy way of saying tree compression, but it's like a very specific type of tree compression. Because obviously we have like DSU path compression, right? Where every node gets like compressed to the root, right? Which is fine and all, like for quickly searching the root, but that's not really what we want for our purposes. What we want is to answer a very general type of query, but like we want to, it's going to be a very specific type of query, but we can do this for very general functions. In particular, we want to answer queries where we have some tree and we want to query a subset of k vertices. And we want to evaluate some function on these k vertices. Obviously, the function is going to take into account the structure of the tree, otherwise we would just be given an array, right? And so if we could somehow evaluate this function on the entire tree in like O of n per se, right? That's fine and all for one query, but what if we had like 10 to the 5th queries, right? Because if we chose our subset of k vertices and we mark them as being important and we do our like evaluation function, that's gonna be, and we do that for every query, that's gonna be O of q times n, right? Number of queries times the size of the tree, which for big bounds could be up to 10 to the 10 if they're both like 10 to the 5th, which is obviously too slow, right? Instead, we want to do something that is order with respect to the number of vertices in our given subset, right? Because if we can do that, then we can do this in a lot less time, because the sum of k has to be bounded in order to actually read in the input, right? So we want to do some type of compression on the tree with respect to the k vertices, such that we maintain the structure of the tree. Like we want to keep some nodes and throw out some others. And we're gonna go over which ones we want to keep and throw out. Because if we have, I don't know, given some tree, let's say our given subset of k vertices, let me just box them. Let's say these are like our important nodes, right? Again, like if we do like this DSU path compression, where we just like throw out all the nodes that maybe we keep the root and maybe we only keep the important nodes, right? We lose a lot of important information in our tree, specifically like where these nodes come from. Because yeah, we know they all come from the root, but at what point do they split off, right? And so this gives us a good motivation to consider where they split off from. And you could guess, like, sure, there's a lot of points they're split off from, but what we want in particular are the LCAs between the k vertices, right? We want to, not only the LCAs, but we want to keep the pairwise LCAs of all the k vertices. So if we have, let me draw a little bit of a bigger tree. So let's say these three nodes are going to be in our important subset, whatever. We take the pairwise LCAs of all these guys. So these guys LCA will be the root. These guys pairwise LCA will be here, these guys as LCA will be the root, but we already counted it, so it's fine. And then we can kind of compress the tree, removing all these guys that are not in our new subset, right? But doing this naively is really bad, because what we had before of answering this type of query in O of q times n, we're gonna have a kind of almost worse, because we're gonna be doing O of k squared, right, plus k per query, if we try to do all the LCAs naively, which is actually just straight up worse than doing the O of n. So yeah, so this is kind of bad, but looks can be kind of deceiving. So it turns out, first of all, any questions so far? Good. Yeah, so it seems that this is really bad, that doing all the pairwise LCAs of our subset of k vertices will result in k squared. Obviously, the number of vertices in our new tree is bounded by n, but still it takes k squared construction time at least, right? But instead, we'll do something a little bit smarter. So I'm going to try draw a big tree here. Okay, I don't know, let's just label these at random. Let's label this really quick. 3, 4, 5, 6, 7, 8, 10, 13.
So is this out only for a labeled tree?
No, I mean, it doesn't matter. You can permute these numbers any way you want. Yeah, so let's say our subset, I don't know, will be like here, here. Let's say we mark, let me write this down actually. We're gonna mark 19, 10, 11, 16, 18, 21, 20. So let's say we're given this query where we have to perform some evaluation function on the subset of k vertices. Obviously, we're gonna try to build a virtual tree on these. So we do all the pairwise LCAs, build that, but that construction is just too slow, right? Instead, what we will do is we'll do some pre-comp. We're going to perform the Euler Tor or Coleman Classic, sort them by their pre-order number, right? So if we do that, let's sort these vertices by their pre-order number. So it would be 10, 19, 11, 16, 21, 22, 18. Okay. So now that we sort them by the pre-order number, here's like the punchline for virtual trees, right? For if we try to get the LCA between any any pair of vertices, it's going to be represented as the LCA of some two adjacent vertices in between, right? And that's really powerful because instead of doing a k-squared construction, now we can do an order k construction. And even more so, we only have to add an extra k nodes, or k minus 1 nodes at most. And this construction, or this is not entirely obvious why this is true, right? Like why is the total number of added LCAs linear with respect to k, right? But we can do like a pretty simple proof, right? Consider some node and like 2 subtrees here, right? Let's say we have a bunch of important nodes in here, right? You're gonna count this as an LCA multiple times, right? We kind of get this equivalence class, if you will. But we don't want to count it multiple times, right? That's too slow. Instead, what we want to do is we just want to count it once, right? So we'll canonicalize, and we'll say we're going to choose a canonical pair from this, so that we don't count this multiple times. So let's just say, let's choose the guy with the latest preorder in here and the earliest preorder here. And it turns out both of these nodes, right, are going to be adjacent in our sorted list up here. Okay. So if we choose a canonical pair for every time this is the LCA for each equivalence class, we only get a linear number of LCAs with respect to our subset. Does that make sense? Yeah.
So you're saying get the pairwise LCAs and then do it again? And that
No. We want the pairwise LCAs, right?
Yeah.
But we've just proven that there's actually at most k-1 unique LCAs in there, and we can do this construction in order to k-1, or we can get all the k-1. So this proof right here, we could get all the pairwise LCAs, right? But a lot of them are going to be repeated multiple times. We don't want to do that because that's too slow. And this, when we're building our virtual tree, we're going to consider it once anyway.
Sorry, I didn't mean pairwise. I meant like adjacent. Across.
Yeah, adjacent.
And then do you do that multiple times?
No, you just do it
just
once.
the once. Okay.
Yeah, you just sort it by its preorder value, then grab the adjacent LCAs from here. We're going to add them to our list of subset vertices, sort them again, and unique them, basically because we don't want duplicates. We could get duplicates, but it's still going to be linear with respect to k. So in this case, we would tack on, let's see, the LCA between 10 and 19, which would be 4. The LCA between 19 and 11, which would be the root, would be 1. 11 and 16, which is 11. That's already in here. Don't need to add it again. 16 and 21. It's going to be 8. 21, 22, 17. And 22 and 18, which is 8. Oh, we already have that in here. So that's fine. So now we're going to sort these again. Let's sort them. We get 1. Actually, let me mark them first. So we have 1, 4, 8, and 17. Right, that makes sense. So let's sort them again by the preorder values. So you get 1, 4, 10, 19, 8, 11, 16, 16, 17, 21, 22, and 18, I believe. Okay, so now we've compressed this tree, or we've only kept the nodes that are important, that keeps the structure of the tree with respect to our k important vertices, right? So if we actually draw the compressed tree over here, we would get something like 1 connects to 4, 4 connects to 10, it's 19, 1 connects to 8, it's 11, 16, 17, 21, 22, and 18. Okay, so we've compressed our tree down to how we started with 1, 2, 3, 4, 5, 6, 7 nodes, and we compressed it down to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 nodes. So instead of having k squared vertices, we notice that we actually only have at most 2k minus 1 vertices in our compressed tree, right? So this is easy, like, to tell, like, from visual inspection how we actually build this tree, but it's not entirely obvious how we do it in code, right? And it's actually a really nice way of doing it, right? We can actually do a monotonic stack sweep, right, going from left to right to actually build this tree. So we're gonna put 1 in our stack, basically, and we'll draw the nodes as we go. We're gonna go. We just traverse this sorted order, right? We go to 4 next, and then we say, hey, is this guy an ancestor of me? And you can do ancestor checks in O1 pretty easily. So you check, hey, is this an ancestor of me? If he is, then then I'm going to be a child of him. Then we move on to the next guy. We see 10. We're going to say, yeah, he's an ancestor of me, so I'm going to add him as my child. And then I go to 19. We're currently here. We say, is 10 an ancestor of 19? It's not, right? So we pop 10 off the stack and we go back to 4. And then we say, is 4 an ancestor of me? It is, so we're going to add that to our node. And then we go to 8, and we say, is 8 ancestor of, or is 19 an ancestor of 8? It's not, so we pop it off the stack. We go to 4, is 4 an ancestor of 8? It's not, we pop it off the stack. We go to 1, and we just basically carry on like this. Say 11, we go to 16, right? And then we have to pop off the stack again because 16 is not a ancestor of 17, so we pop off the stack. 17, 21, 22, and all the way to 18. So you basically, yeah.
So, do you have to do this after getting all of the LCS, or is there a way to do both at the same time?
It's just way easier to do like this.
Okay.
Yeah, I mean, there's no point, like, you probably could, maybe, but it's so easy to do this, because once you add in the LCAs, sort them, and unique them, then the stack sweep is, like, super easy to implement. Yeah, so.
How are you doing it? Is ancestor check?
Yeah, so when you do, so we already did our Euler-Tor pre-comp, right? And part of our Euler-Tor pre-comp is we have, like, the start, right? For every vertex we have start and end, right? To do an ancestor check, we just have to check if U is an ancestor of V. We just have to check if start of U is less than or equal to start of V, right? And end of V is less than or equal to end of U. Right? You're just checking if it's in its subtree, basically. It's a subtree check.
Are we always going to be including our root in our virtual tree?
Not necessarily.
So like if you're like contained within an entire subtree, you would exclude your root?
Yeah. Yeah, so yeah, your root might not necessarily be in a subtree. All you actually just need are the LCAs. So the root is going to be actually the subtree that contains every node at the lowest possible level. But yeah, that's how you do the construction of the virtual tree. Does that make sense?
Why does 10 come before 19 in the pre-order traversal?
I mean, it doesn't actually matter. Like, we could, yeah, you're right. It should really be yours. But we just put it over here. Or it doesn't matter.
What's the time complexity of like building the virtual tree?
Yeah, so assuming we do LCAs, we can do LCA queries in O of 1 with RMQ, whatever. It's going to be like K log K, right? Because we're going to sort these K vertices based on their pre-order. Then we add the linear number of LCAs, then we sort those. So it's going to be like order of K log K per query. Make sense? Any other questions? Okay, does the construction make sense? Like the stacks would? Okay, that's good. Yeah, that's virtual trees pretty much, and say, yeah, they're fairly easy to build. Now we're gonna look at some problems that we can do. Some virtual trees. Oh, one really quick thing. So basically what we reduced this down to is saying instead of doing O of n per query, we can now do O of k log k per query, right? And this is really nice because the sum of k log k is going to be bounded by your input. Like obviously you have to read in at least k things, right? So this is going to be like bounded by like 10 to the fifth log 10 to the fifth. So this is much faster. Okay. Now we're going to look at some problems. Also, I have to mention that you can find this code in Cactal, like tree compression code. I don't like using Cactal, so I mean you can use it if you want, but I recommend you write it. Okay, start off with a nice problem here. So the problem is you're given a tree, given some tree, right? And you're given a bunch of queries, and in each query you're given like you're given n nodes per query, and in those n nodes, you want to check if they form a linked list or not. Like you want to walk from vertice. Yeah, you basically want to check if they form a linked list. So let's say we mark these nodes as being in our subset, right? Obviously, these do not form a linked list because you have to go here, because you have to come up here, then you have to walk down here, and come back up. So you revisit a node multiple times, and basically you don't want to do that. So you want to check if, but if we just like erase this, maybe like this, then this does kind of form a linked list because we move up here and we move down. We don't revisit any nodes. Okay. So does anybody have any ideas?
Build your virtual tree on your nodes,
Okay.
and then check to see if every node in your virtual tree has either degree 2 or if your 2 endpoints have degree 1.
Yeah, that's very good. We're gonna just build our virtual tree, and we notice that
Are there queries to this problem?
you're given Q queries, and in each query you're given a subset of nodes, and you have to check if they form a linked list or not. So yeah, what Tyler's saying, you form the virtual tree, and it's going to be only a linked list if and only if you get a structure kind of like this, right? The root node is the only one who's allowed to have 2 children, and everybody else has to have 1 or 0 children, if that makes sense. And it's going to be connected because it's a virtual tree. But if we had something like this, obviously this guy's not the root, but he has more than 1 children, so this is not going to be a linked list. Does that make sense to everybody?
But wait, you have to do this for all of the queries, but you pre-comp the virtual tree, don't you?
No, you build a virtual tree on every query.
But wouldn't that be too much?
So
Are the queries limited by n as well? Like the sum of?
Well, yeah, you have to read in the input, right?
Oh, sure.
Yeah. So that's like the main idea of virtual trees. You have to read in the input anyway,
Yeah.
and then you can like build it. Any questions? All good? Okay, nice. So it's actually nice because this isn't actually the intended for this problem, but virtual trees are super nice because even in problems that they're not intended, they just make them so much simpler, right? They get rid of casework, like almost all the casework on this problem. Yep. So really nice technique to use. Okay, we're gonna move on to a little bit of a harder one. Let's say you have problem. Alright, for this problem, you have a kingdom and it has n cities in the kingdom. Okay. And the cities are going to be represented as a tree. Right. And we're in this problem, we're also given a bunch of queries where in each query you're given a bunch of nodes. You're given k nodes, you're given q queries and k nodes in each query, and we mark these nodes as important. So for example, let me just color in the important node here. Okay, so let's say these three are important nodes. We want to somehow partition the tree, or we want to cut the tree such that no two important nodes are in the same partition, or like in the same group after our partition. And we want to do this, and the way we do this, the way we partition it is we basically remove nodes from our tree. Like for example, if we remove this node here, these two become disconnected. If we remove this node here, these become disconnected, so now they're all disconnected. And we want to do this with minimal cost. We want to somehow partition this tree with minimal cost such that all these important nodes are in different groups.
Can we remove the important nodes?
No, you can't remove important nodes.
So two important nodes can't be next to each other then?
Yeah, that's true. So if it's impossible, print out -1.
Oh.
So yeah, what Thomas was saying is if you have two important nodes next to each other, obviously it's impossible and just print out -1. But does anybody have any ideas? This problem?
What exactly is the cost? Like, are the nodes weighted, or is
No. Sure, let's wait. Yeah, the cost is the sum. Let's say the cost is the sum of the weights of all the nodes we remove. Any ideas? And we're given q queries. We mark, and for each query we have k. We mark the k important nodes in that tree, and then we unmark them for the next query. And we want to do this. We want to answer this minimum cost for all q queries. Any ideas? Yeah.
Why, it feels like it should be like number of edges in the auxiliary tree, but I'm not sure why it's not that. Feels like I'm missing something.
Sure, but let's say we weight our nodes, right? It's gonna be, say we're gonna weight our nodes.
We can get that.
Can you like make the edges in the virtual tree be the min of the weights of the nodes on the path between two of the important nodes?
You could, but why is that helpful? Because we're cutting vertices, not edges. Yeah.
Well, it's like you're never gonna have two nodes next to each other. So any edge can be like any edge you can represent as like some nodes in between them, because we already shown that there's gonna be nodes in between them.
Yeah.
And then like if you in the construction of the virtual tree, like as you're doing the stack sweep, you can like grab the min on path and like set that edge weight, and then in your virtual tree it should just be the sum of those edge weights as Sachin was saying, I think.
Yeah, very good.
So I just like
You're kind of missing one part, but yeah.
Yeah, I don't know if you mentioned it, but like if like you only have to consider the nodes next to each other in the sorting, like when they're like sorted in pre-order. I'm pretty sure that's true. And if there's like an LCA, if if you consider two nodes and like one's not an LCA of the other, then you have to take like the min up from like the path from the first node to the LCA and the min from the path from the LCA to the second node.
Yeah.
And remove one of those to disconnect.
Yeah, that's a pretty good observation. Yeah, you can certainly do that, or we can do like that. Requires some casework, but let's try to avoid as much casework as we can. So we've already determined the case where we have things next to each other, so we know none of them are going to be next to each other. So we can build this virtual tree, right? So like, let's pretend our virtual tree is something like this.
Oh.
Yeah.
Oh yeah.
Some of them are LCAs.
I forgot how to do. I forgot how virtual trees work.
I'm thinking some form of like tree DP,
Mhm.
where we start at our root and we're either going to, if we're not a special node, we can either remove that node,
Yeah.
which would disconnect all of our children,
Mhm.
or we have to like remove all of the edges.
Yeah.
And we can store DP of like whether or not we've already disconnected us from our parent.
Mm-hmm. Yeah, that's almost pretty much the solution. So yeah, so after we do this virtual tree, we're gonna compress nodes that we eliminated, like doing a range sum query or something, or like a range min query. I mean, because if we have like a couple nodes here, right? So our first part is when we do our virtual tree, these are gonna get compressed, right? But we still have a bunch of options. So instead, we can do like, I don't know, we can do binary lifting to get the edge weights, right, the min of them. So we're gonna have some weights on these edges and the nodes, right? And it's important because what Thomas was saying was really close, but some of these nodes are not gonna be important in our virtual tree. So we're still gonna have to do some type of tree DP, where we do something on the edges and the nodes. So yeah, we could have like a DP of like, is there like top down, we could say, am I connected to an important node? And you have like two options here. You could either cut it here or you could continue down. That makes sense. And yeah, that's pretty much all you do for this problem. Does that make sense? Good. Yeah, so you, so yeah, common trait of these virtual trees is when you compress because what virtual trees are basically doing is you're compressing the linked list between them, right? But you lose some information when you compress. So it's typically you have to have like you do some binary lifting or some RMQ to actually get like the information like that we lost, like either the sum of the nodes or like the min of the nodes, or in this case, or the max of nodes, stuff like that. And yeah, so it's a really simple problem. Or not a simple problem, but simple once we do this virtual tree.
This problem is trivial.
Okay. Another problem here.
Wait, was that the intended solution for that problem?
I think so. Yeah, I think it was intended. Actually, like a lot of times in virtual trees, you can say you're not doing this intended thing, like, but what you end up doing is something that mimics a virtual tree anyway. So like, why not build it anyway? So it's really nice. Okay, so for this tree, or for this problem, you're gonna have a tree where you have a bunch of nodes and a root, or you don't have to make it a root, but we're gonna root it anyway. Right, and you're gonna color these nodes in different colors, and and you have some function for some path on the tree. You're given a function, like f of uv, which is the number of unique colors on the path, okay? And then you want to find the sum of this function over for all pairs u and v. So any ideas?
How many numbers or how many colors are there?
There can be up to 10 to the 5th colors.
Is this queries or like? each
No
one?
queries.
Okay.
You just have to put one number. Yeah, so this problem's a little strange, right? And here usually we're used to like being given some queries and a subset of k vertices, right? But in this problem we don't have any of that. We just want to print out one number. Any observations at all?
Well, we can kind of like force there to be queries in some sense by like treating each different color as like a query.
Yeah,
Modeling
that's
the
very
virtual
cool.
tree on each color.
Yeah, that's really good because we know that the sum of the number of colors is bounded by the number of nodes. Actually, it's going to be less than or equal to the number of nodes. So we can kind of create these queries ourselves, right? And we can build a virtual tree on each color, right? And it's really nice because when we build our virtual tree, right, for some color, actually, first that, since we're doing a summation here, we can actually do like a contribution to a sum solution, where we contribute the function over this color to the sum in total, because they're kind of independent, right? Like two colors don't actually mix with each other, like they don't matter pretty much. Oh, you only care about colors of the same type, right? Okay, so we reduced the problem to doing contribution to sum over every color. And we probably want to build a virtual tree on these colors. Any suggestions what we do here?
I think like you have to get the distance, like I think you have to weight those edges, like, and it's like the sum of the weight choose to, maybe something like that. Like that's gonna be the number of different queries where like there's some node of this color like on that query, and then it's like kind of like it's like linearity of not linearity of expectation. What you said with the contribution, where if you like take that for each virtual tree, that should like sum to the same answer as if you were getting the distinct colors. I might be off by a bit on the math.
Yeah, you're super close actually. Yeah, so when we build this virtual tree, we're not all the nodes are going to be of this color, right? Because we're gonna have some LCAs that are gonna be different color. Right, so let's just say like it's our tree right here. And what's also saying is we weight the edges with how many nodes we've compressed in here. So yeah, so we can like weight this with weight of I. But still doing
Yeah, so the thing is, not every like child of a subtree is going to be in the virtual tree, but it also, like for a subtree, it could still be the LCA of two different things.
Right.
So it's more like you also, for every node in the virtual tree, you need to like find the like real subtree size for each child, and for the ones that are in the virtual tree, it's going to be the edge weight. Otherwise, it's going to be the full subtree size.
Yeah, it's really good. Yeah, so we actually have like a bunch more information that we have to store. But something that's really difficult about this problem is we're trying to count the number of passes that contain at least one of these, which is kind of maybe a little bit difficult, right? So instead, we'll do some complementary counting, and we'll say how many paths do not contain this color, and subtract them from the total number of paths. And it turns out if we do that, like if we do the compression with the like getting all the weights and stuff, we can do like pretty easy like DFS at that point to get the number of paths that don't contain this color, subtract it from the total number of paths, and add that to your contribution, right, towards this final answer. Does that make sense, everybody? Good? Yeah.
where are you getting? So is it like for each edge weight, like choose two on the edge weight since that's all the nodes in between that won't go from like either guy?
Yeah, because you're gonna like
as well as the subtrees that are not.
yeah all the subtrees as well. Yeah, you need the subtrees because you can they can still be on the outside as well. But yeah.
The edges don't tell you you have like components of like edges that are like because if you have a node that's like not of the same color, like all the edges connecting to those nodes connecting to that node are like in the same component.
Yeah, so yeah, you basically get a bunch of components here. It's a little bit tricky to go through, but it's not too bad. You know, once you realize that you're basically counting all the nodes in between, like these important nodes, you basically get a bunch of components and do some math or do a DP, do the DFS. Not too bad. Yeah, it's a good problem, and this is a good problem because it's not super obvious that we want to use virtual trees here because we're not given the queries, but we make our own queries instead, so that simplifies our problem. Yeah, that's this problem here. Yeah, so.
I don't think you actually need like LCAs to build a virtual tree in this case.
Yeah, so, expand on your point.
I think you could do like, because it's offline,
Mm-hmm.
we could just do a DFS
Mhm.
and like store some array of like the guy above us with this color.
Mhm.
And then like construct all of them in one DFS.
Yeah, that's
But, like
good.
without
Yeah.
even constructing them.
Yeah, you could do that as well. You don't actually need to like do this like LCA construction, but it is pretty nice. Like if you want to do like without any thinking stuff, just do it.
Done it.
Right?
You don't think it's
You don't want to think as least as possible, right? In these scenarios. Yeah, you can just do that.
It's a lot of heck.
That's respect.
But yeah, you don't actually need to build like this full LCA construction for this problem. I got one more problem here. It's gonna be maybe a little bit similar. You're given, okay, so yeah, so in this problem, you're gonna be given a tree. It's gonna sound super familiar. This time you have colors on the edges, and you want to count, and you have a function for some path, right? Which is the number of values, number of colors on this path, such that there's only one color of, there's only one of this color on the path. And if there's only one of this color on the path, you add one, basically. And it's the sum of all those on the path. But yeah, you have colors on the edges this time. Does that make sense? So any ideas?
Same solution.
Huh?
Is this the same?
No, almost the same, except there's a couple minor differences. You have your colors on the edges this time, and you're trying to, the function's a little bit different. You're trying to find the function for some path is the number of things that appear exactly once on that path, and you want the sum of all those. So it's not at least one, it's at exactly one.
Do almost the same solution.
Yeah. So what's your idea?
I was thinking it's like, well, actually I had to get two ideas.
Okay.
One of them is like we could do something similar where you basically like do dynamic connectivity offline and remove all the edges of some color. And then you can take the, I think it's like product of some of these subsets or subgraph sizes.
Yeah.
I think we could also do that with a virtual tree by multiplying ourselves by the sizes of our children's
Sure.
trees.
Yeah, you could actually do this with dynamic connectivity, like your segment tree over time, if you want to. So yeah, that's a valid solution. Or we could we could build these virtual trees, it's a bit weird since we have these on the edges, but we can like do a nice technique where we split each edge into 2 edges and we insert a node in between. And now suddenly we can do like a virtual tree on these colors. And it's going to be, once we get a virtual tree on some color, right? Something, we mark them as whatever. Now we only want to consider paths that contain exactly one of these guys. But we could like do some complementary counting again, like where we say we like only care about, or no, we don't want to do complementary counting here. Sorry. Like we can do the kind of like a DP, right? Because we want the number of paths that cross to exactly one of these guys, right? Instead of 0 of these guys, like for the previous problem, we want the number of paths that cross to none of these, but we want to now say how many paths cross through exactly one of these. And yeah, it's almost the exact same as the previous problem, except here a little bit more casework. I think you could do like a DP, probably, or like a DFS. But yeah, that's almost the same as the previous problem. Any questions? All good. All right. Yeah, that's kind of almost. Yeah, that's pretty much the last problem I had. I want to give like some homework for you guys. This is gonna be. Maybe you might find this a little more challenging. We're going to build. So let's say we have a graph of infinite numbers, right? All the natural numbers from 1 to whatever, infinity. And we're going to build this graph such that there's an edge between a vertex x and the vertex x over f of x, where f of x is the smallest prime divisor of x. So we get this graph where we add these edges, and we basically have, in our input, we have like a bunch of fragments, like 10 to the 5th fragments. And we're basically given an array, and we're going to say like the first fragment is located in vertex k1, second one in k2, k3, k4, blah blah blah. But a nice restriction for this problem is that ki is less than or equal to 5,000. And basically, we want to pick some node in our graph such that the distance from moving all the fragments from these nodes to that special node is minimized. Okay, this problem makes sense to everybody?
Can you repeat that?
Yeah, so we're basically given like 10 to the 5th fragments. Here, like an array of fragments. And we're going to say the first fragment is in vertex k1, second fragment is vertex k2, vertex k3, so on. But these, I misspoke. They're going to be in vertex k1 factorial. Yeah, that was my mistake. Yeah, we're given the vertices as like, it's going to be located in k1 factorial, k2 factorial, k3 factorial, and k4 factorial. And we want to pick a node in our infinite graph such that the distance, like the sum of the distances from the fragments to that special node is minimized. Like we want to move all the fragments to that special node, if that makes sense. So it's, so you have a graph where like these are the edges and these are where the fragments are located, and you want to minimize that and just output it. Does that make sense to everybody?
Are you outputting the node or the distance?
I'll put the distance. And yeah, that's pretty, I wanted to think of this problem. It's a good one to think about. Yeah, that was my lecture on virtual trees.